Really delighted to be here at the Biodiscovery Institute at the University of Nottingham with Professor Chris Denning.
Lovely to be here as well.
So Chris, could you briefly tell us a little bit about your work and what you're aiming to achieve here?
Yeah, absolutely. So our work really comes down to stem cell technologies. What we're really interested in doing is trying to use stem cells, human stem cells, in a way that allows us to understand the genetics of the heart, how that can go right or how it can go wrong, and also how different drugs might affect those processes of the heart. And so ultimately what we want to do is have a system where we can make better and safer drugs. We know more about human disease so we can try and fix it, and ultimately lead to next generation technologies that I'll be delighted to explain to you.
Well, please do.
Yeah. So one of these technologies, the first one that we use, is called human-induced pluripotent stem cells. Now that's a big name for something, but what it means in reality, and there was a Nobel Prize won for this technology just a few years ago, it means that we can take a skin biopsy from a patient, and that's a small one. It's about the same size as the head of a matchstick. And then we can put that in a dish in the lab, and we can use genetic trickery to convince those skin cells to become stem cells. And then after that, we can use more trickery to convert the stem cells into heart cells. So you start with skin and you end up with heart. Now, the beauty of that is the genetics of that skin cell is the same in the heart cell. And so instead of having to go to a patient or to use animals or anything like that, it means that we can recreate human disease in a dish, and then we can ask specific questions around that disease all in a dish in the lab. And because that overcomes some of the key differences between humans and other animal species, it means that we want to aim towards a more reproducible, realistic system for human disease. So in other words, make a human system to treat a human disease.
That's so important, isn't it? So is that taking us closer to personalised medicine as well then?
Yes, it is, and that's the holy grail, if you like. And so let's just fast forward by 20, 30 years, whatever it might be. Now imagine you've got a genetic disease of your heart, and we know what that genetic disease is, and it's making your heart fail. Now imagine we can go through this clever genetic trickery and we can make lots of these heart cells. But along the way, we use technologies such as gene editing to correct the mutation within those heart cells. Now we have your genetics that have been corrected, made into heart cells that will be a better match for you. And so imagine that, where we could then not only understand the disease for making new drugs, but in the future, potentially put on heart patches to make your heart work better, but that's been a corrected patch as opposed to the same disease cells. So let's dream into the future. That's the kind of technology that we want to aim for.
That's such an inspiring vision. So how far away do you think that is?
So it depends on which part of this spectrum we're aiming for. So it's something like that example I gave you, that's going to take a long time to get to. The first kind of trials to determine whether stem cell derived heart cells are effective in human patients, they're underway. But it's very, very early stages. And so that's going to take a number of years. To get to that stage where we start to do personalized correction and so on, you're talking decades rather than single years. But then flip that around and start to ask other questions around the current drug discovery pipeline. You identify a drug in a pretty artificial system. You then take it forwards and you put it through a bunch of animal systems, many of which aren't that accurate.
No.
And all of those drugs then go into clinical trials. Most of those drugs fail when they get into clinical trials because humans are different from our other animal cousins, okay? And so there's a lot of waste that goes along the way. Now imagine we could do a situation where we replace some of those animal models with human stem cells. That is already starting to happen. And so as a specific example, we and other people work with a range of pharmaceutical companies, and the other people that you've heard from today, people like Kate and Kavita, they're working with companies like GlaxoSmithKline, and we've worked with them like that company before as well. And we've been able to show that some of these stem cell derived heart cells, this mini heart project, if you like, is able to do better than some of the animal models. So one of the tests that is used to check whether drugs might cause adverse activities in the heart is known as the rabbit ventricular wedge. It basically takes pieces of a rabbit heart and it tests drugs on those to see whether that heart goes wrong. Our work, which is really a co-creation between us and many other people with GSK, has convinced GSK to stop using that rabbit experimentation in at least parts of their pipeline. For me, that's a huge success because it shows that partnerships working together can get to the stage where you're not switching things off overnight because the regulators won't tolerate that, but you are working in partnership with people to show that these kind of model systems can improve on what we have at the moment and ultimately lead to the replacement of those animals. So we know that. Now let's take a step forwards. Imagine we could then create a whole panel of these human-induced pluripotent stem cell lines that reflect 100 different genotypes, ethnicities, populations around the world. And then you run the drug through that whole range. That kind of technology, that's impossible to do using current systems. What we do is we use these inbred animal strains. In many cases, we then go into limited clinical trials that might just use a handful of patients. But imagine you could do an in vitro clinical trial with 100 patients of diverse genotypes. That would tell you whether drugs are safe or not. Now, if we can get to that stage, who wouldn't want to invest in that?
Absolutely. So Animal Free Research UK is all about creating a world where human diseases are cured faster without animal suffering. So it sounds to me like what you've just described, that's how we're going to get there.
Exactly right. And the other thing everything comes down to society and economics. And if you can provide a solution that has societal benefit, in other words, you're making safer drugs, and in addition to that, you can create something that's economically favorable for the pharmaceutical company, then that's going to be a plus. So if you look at the information that's out there, back in 2015 for animal use in the drug industry, there were thousands, if not millions, of animals that were used. And in total, that cost in the order of about $11 billion in a single year. And so, even putting to one side the effect on the animals that we used, if you could then go to a system where you could reduce those costs by 10%, 20%, 50%, that becomes attractive, not only from the messaging that it sends out, that companies are trying to use less animals in their experiments, they're using a better technology and they're reducing costs. And it's that kind of positive messaging that we need to get across, because you look at all the political things that have happened in the last 10 years, people follow positivity. They don't follow negativity about this is bad, this is bad. They follow positivity. And so if we can sell very positive, forthright and honest messages of how this is better, then that's how we're going to win hearts and minds and ultimately change the legislation that's there at the moment.
Absolutely. It's a win for science, it's a win for patients, it's a win for animals, it's a win for the pharmaceutical industry.
Exactly right.